Okay, I hope it's audible in YouTube. So you can just confirm in chat if it is. So ಇದು audible ಇದೆ ಅಂತ YouTube ಅಲ್ಲಿ. Let me share the screen. ಕಾಣಿಸ್ತಿದೆ ಈಗ?
Hmm.
Okay. So I think we'll just repeat certain topics because earlier in yesterday's meeting I came to know that uh, like the video got ended in between. So we'll just go through it as a recap. Any other people? Okay, I think only we two are there. In YouTube, I think only Anudeep is there. Okay, fine. So yeah, just check whether it's being recorded in YouTube. Voice there, stream.
Anyone expect to come or like did
No,
they
we will
message?
just start off because it's a revision of yesterday's topic, right?
Okay, okay, it's
So
fine.
it's not an issue for us. Okay. So my screen is visible? No, right? I'll just present it again. It's visible in Teams right now.
Hmm.
Okay. So I think as we discussed yesterday, we touched upon mean, median, mode, range, variance, like different parameters of statistics, where where it is much more useful in analyzing any problem, which is a part of descriptive statistics. Okay, how do we describe a particular problem? So we can use certain statistical parameters to describe a particular problem. So what would be those? They are nothing but mean, median, and mode.
Hmm.
Okay, so these are basic measures of central tendency. That's what we call, where we try to understand how the data is distributed, or what is the nature of the
Right.
data or behavior of the data. Because
Hmm.
only if you understand the behavior of the data, you're able to, kind of solve a problem, or at least understand the nature of the problem to solve it better, or at least it describes the problem better so that you can solve it. So I think we took an example yesterday where we understood what is mean exactly. So we had a data set of shaft diameters, and we understood what exactly is mean. So it is more of a summation of all these data points with respect to the number of data points. So that gives us the mean value. So what does it mean? It means that it takes the average value of all these things, and it is generally helpful, or maybe even helpful, when we decide some shaft tolerances. Say in case of interference fit designs, where we have certain tolerances to be designed, and we want some average value of the shaft diameter to be maintained within a certain tolerances. So in these cases, mean can be used. Okay. And next measure was median. So what exactly was median? Median is nothing but kind of finding a middle value in a particular data set. So for that, first what you will have to do is sort the particular data set what you got over here into ascending order, okay, from smallest to largest, and then find the middle value of that and take the average of that. Average in the case of even number, suppose if it's odd number, you can directly take the middle value of that, like kind of middle placement value, right? And mode is nothing but the most occurring or the frequently occurring value, or which is repeating, like every now and then, how many times a single value has been repeated. And coming to range, it is more of max value and min value, kind of difference between max and min value in a particular data set which is given here, right? And variance, it tries to understand the variation from the mean value what we calculated. So it is more of individual data point, that is xi minus x bar, which is the mean which we calculated earlier, kind of summation of that with a squared term divided by n minus 1. So we can see these are individual data points what we had, and then we identified the deviation of individual data point with respect to the mean, and then we square it, right? So that is what it calculates and gives it to us. So the square root of that particular variance gives us the standard deviation. So it means that how much is it, like say, varying from the mean value. So I think we didn't discuss the difference between that yesterday. So I just pasted it here. So when we see here, it is more of square term, right? So generally, when we have the data, this might be in terms of this particular data. When we square it, becomes square. So there is no consistency in data in understanding the spread of the data. So when you square that term, it comes back to the original unit. That's when we are able to understand how much is the spread of the data with respect to the mean. So standard deviation is more like say useful in interpreting compared to variance. That's why we try to take the square root of that. So it's more of a distance, right? I think we have even a distance formula where we calculate between 2 points, like say x1 and y1 and x2 and y2. We have distance formula where you like take the difference between the two different points, y2 minus y1 the whole square plus x2 minus x1 the whole square, and you identify the distance. So similarly, when you take the square root of that particular variance, it tries to give the distance between the point from the mean value to the original point, right? So it tries to give more of a
mm,
distance kind of thing. And next, I think we even discussed kind of got an inference. What does these different measures of statistics mean? Like, what would mean diameter mean? So we can say if the mean diameter is around 25.003, so it might be possible that there is a very good like say machining capability in the production, because it is meeting the expected like say optimum shaft diameter of 25 even though it might be within the tolerance limit. And standard deviation with the very low value, it also says that the shaft is consistently produced. It means there is no much variation in the production of the shaft with respect to the diameter. Maybe machining is very good, or there might be no like say quality issues related to burrs or something like that. And range helps us to understand the tolerance range in case of this shaft manufacturing. And if there are multiple modes, then it might be possible that it's showing that there are many shaft diameters which are having consistency, like it is consistently produced with the same shaft diameter. Similarly, I think this kind of metrics also helps us to understand whether the manufacturing process is very much stable and it is more repeatable. Like the kind of quality metrics, is it more stabilized, or how many times it is repeated, or how is the distribution of the quality metrics? All those stuffs we'll be able to understand. So just as an example, I think we had even discussed yesterday that like we can see the mean and median are very much nearby here, right? And since we calculated mean and median earlier here, we can also say that for the variation of the diameter, what exactly would be the expected diameter, and how much is it varying, and what kind of distribution it forms. Kind of not exactly normal distribution, but it has a kind of little bit of normal distribution. And what happens if I have an extreme value? Like in this case, next case, I just put a little bit more value, and we can see there is an outlier here, and how the mean is getting shifted, and how mean value is very much sensitive to it, right? How it is changing. So we even discussed this yesterday, and how outliers can be seen even in the box plot. I think up to here we discussed very well in the last class in the recorded session. I think after this there was some problem. So do you have any doubts up to here? No, right?
no, no.
No, right?
So if, for example, if you want to check it in a uh, perspective of the formula, so how it's like mean is more, you know, uh,
Huh?
prone to D. So it's like when it
Like prone to?
much more sensitive.
Ah,
So
yeah, yeah. I think I just yesterday showed you in the code. I think it should be having somewhere here. Somewhere here, yeah. Yeah. So we had seen it here, right? I'll just
mm,
reduce it. Okay, let's say I remove this data, right? So you can see now we have very good data, right? There are no outliers here.
mm,
It's not able to identify an outlier, right? We'll just add some data here, maybe roughly around 26, then 26.03. Okay. So there is some data here. So you can see
mm-hmm,
mean got shifted here. Median variation is very less, right? Like that's what I have shown over here. The median
mm,
variation is very less. Let's say we have still more higher diameter value. Let's say well, this is more of 35. So now again you can see it is changing drastically
mm-hmm.
compared to this.
Correct, correct, got
Yeah,
it. Yeah.
yeah.
So
So
it's
this,
like it's like, for example, if you have consider a salary of a person of 50, 60, or
yeah, it's like
suddenly if a Yeah, somebody have a salary. Suddenly, if one guy's salary is like
yeah, very
one
high,
lakh or
then
two
it
lakh,
will shift the mean.
the mean will, yeah,
Yeah,
exactly. So
suppose let's say we have value as 100.
mm. So it has to average out, right? So
Yeah, yeah,
it will average out. It will put some bits of that in
yeah. So
everything,
you
so
can
that the
see
average
mean
will
is 28
put up.
now. So
Correct.
median is almost nearby, same only, right? It's not
Mm,
changing much. So we can say mean is
correct.
very much sensitive to the outliers.
Mm,
So next point after that, I think then we even discussed on some other point. Yeah, skewness, right? Yeah, next point was skewness. So when do we say that the data is right skewed or left skewed, or it is more of a symmetric
mm,
data? Okay, so basically skewness helps us to understand how the data is distributed, kind of measure of asymmetriness. So when mean is greater than median and mode, okay, so it means it is positively skewed. I think yesterday I didn't update it. It should be left skewed and right skewed. Okay, I think it should be at least we should be able to see it in some internet. Yeah, so you can see the data skewness here, right?
mm,
Yeah. So this is more of symmetrical distribution where we have mean value equivalent to mode value and median value. It means it is a normal distribution or symmetrical distribution, right? And
mm,
so suppose, as we said, if like say mean value is very much higher than the median value, like kind of like in this case what we had seen, right? Then it might be positive skewness. And if mean value is less than the median value, then it is negative skewness. We can just check it. In this case, mean value is greater than median value, right?
mm,
So that is what this represents, right? Positive skewness. So you can see that distribution, right? It goes high here and comes here down.
mm,
Then we'll just check if it is possible to reduce it one something like this. So what happens? Mean got shifted on other side. So the skewness got changed right here.
mm,
So it represents the negative skewness here, where mean value is less than the median here, right?
mm, mm.
So we can see two outliers here now, 26 and 1 on either sides. One
Right.
is here and one is here. Okay. So that is what skewness meant. And next we like understood what is kurtosis. So kurtosis is nothing but it again describes the shape and peakiness of the distribution. And we have again three terms in that. That is mesokurtic, leptokurtic, and platykurtic. Right. So what does that mean? Is mesokurtic is more of normal distribution, and leptokurtic is like which is having a very sharp tail or like a
Mm,
very sharp peak, and will be very much thin. And kurtosis value will be generally greater than 3, and platykurtic is it is having sorry like leptokurtic is having heavier tails with a sharper peak, and platykurtic will be having thinner tails with a flatter peak. Okay, I think before that we had even discussed a point why mode can't be used for discrete data. Why mode can be used for discrete data and why it can't be used for continuous data. So the reason is because continuous data it is like continuously varying, right? We can't have a repetition every now and then. Only if you bring down the decimals, like say you have decimals up to I mean 25.0434 something like that. When it keeps on changing, there is no repeatability of the same value. But when you bring down the decimals, then there is a repeatability, and then you may be able to calculate the mode for continuous data, which is very for a very smaller data set. But if it's a very larger data set, then it becomes a very good, very like problematic situation because it will be more of a flushing of the data. So it is very difficult to calculate mode for continuous data if you bring down the decimals. So generally, we don't take mode for continuous data, but it works very well for discrete data. And we understood even how can we convert continuous data into like say binning and convert that into discrete data, where I took example of temperature, right? Temperature with
mm,
respect to Young's modulus. So a range of Young's modulus can be binned with the temperature range and then converted continuous data into discrete data, saying that the for a particular temperature range the Young's modulus doesn't change much, right? So that's part of feature engineering which will come later. But This will also help us to understand whether how can we convert continuous data to discrete data, and from discrete data how can we calculate the mode, and how can we check the skewness. And I even explained, I think, even how can we measure the skewness in terms of data. I think I'll just show it again, where we, like same the mobile example where you try to balance with a CG. So generally this is more of a normal distribution if you balance at the center, and if you add more mass here, then the data, it means more data shifted towards towards my right side, and that will show a skewness. And if it's the data shifted more towards left, that will show more of other part of a skewness. And kurtosis represents more of how much load is getting applied, and it represents that peakiness of that particular data distribution. It's more of, if I want to convert in terms of mechanical analogy, it's more like more the load, more is the peakiness of that particular data, right? So till this, do you have any doubts?
No, no.
All right. So we said what would be the alternative for like say this kind of continuous data instead of mode. So we can use KD methods or histograms or something like that to understand the data pattern behaviors. And then next we took certain examples to understand how does or how to analyze kurtosis, right? Where we have three different data of healthy and some defect, that is certain impact, as well as abrasive behavior of a surface finish, or maybe for a particular product. Okay, so this particular data represents more of a normal distribution of the vibration, and this represents more of the skewed data. Both are on same side. Okay, I think that would represent more of positive skewness, right? So this is representing more of positive skewness, and it even represents the kurtosis in a similar way. So we analyze this, and then we saw that the amplitude which is having very high amplitude here, right, that is having very high kurtosis value, right here 9.44. And even coming to skewness, this is having more data because the amplitude varies just only between like say too much between these two values, right? We calculated mean median for this individual data. We try to understand how much is it varying, so we can see even the amplitude is varying only between that data, and more data is concentrated only between that particular amplitude range. So next, then we tried to just summarize those things, right? And then we had a problem to solve, which we solved yesterday. So would you like to solve the problem again for this, like where we had three different data, right? And we tried to understand what would be the skewness for this, right? I'll just zoom out again. Yeah, I think okay. Yeah, I forgot other one point. I showed other one problem where we could see that there's a high vibration levels for a particular system or motor bearing, and then by giving a support, how the frequency got shifted and amplitude got decreased, right? So where we had initial frequency with a very high peak here, and this peak was very much high, so that the minor vibrations got, like, it was not visible too much. Just because of this addition, the amplitude got decreased, and we are able to see those minor peaks here, and roughly from 30 to zero point 0.6 it got reduced, right? I think that is what it shows here. We are able to see that here, right? Decrease in amplitude, and that minor variations got somewhere matched here. So these things can be analyzed with skewness and kurtosis, right? These particular data, the amplitude, as I said, uh, even the frequency curve, we'll be better able to understand how the amplitude changes. Like say more peakiness, which means that it is like too much. I mean, very less damping and too much high amplitude. I think I have saved some data here or something. Let's see. Not sure I've saved the link. Yeah, we have a couple of links here which I showed yesterday. Yeah, so we have certain motor sensors measured here, right? And how do you data acquisition, and how AI is useful for that? And what are the other measures compared, like statistical measures, which we can use for vibration analysis, right? Where we can calculate the RMS values, the peak values, crest value, kurtosis, crest, yeah, crest factor. right? So these will also help us to analyze the vibration data pattern, right? And even performing FFT or PSD also helps us to do or analyze the data. So this is one paper. And I described even about other paper where they were trying to understand the flange mounting area, the vibration pattern of that, and understand the characteristics of that. They place the sensor here and try to understand how the bracket is behaving with respect to the boltings. So they had different measures. So they had even checked the anomaly over here from compared to the normal vibration pattern, right? They try to extract certain features and have some statistical parameters here to understand that, and plot the skewness as well as like say kurtosis. I think you can see it here for normal data and abnormal data. How does it vary? How does that particular data shift, right? And different statistical measures what they did, like they did even hypothesis testing analysis, and they measured t score for that. So this will be covering in upcoming classes. What does this mean, hypothesis testing and t score? So they use these different statistical methods to develop or analyze the problem. So you can see how it's like how can we apply statistical machine learning topic or even classification. So this is a classification metric, right? How can we use those things for analyzing a problem? So all these are classification metric, like they try to classify different outcomes, precision, recall, and all this stuff. So these things will be again discussed in upcoming classes. And okay, not much into this. Yeah, I think even this particular video also helps us to understand how do they do condition monitoring and understand different parameters and all this stuff. So I'll just share this data. Okay. So you can see there are even other parameters which they are creating and trying to analyze the data. Okay, so once after that, I think we'll just try to solve this problem again. Yeah, so I think we had this problem where we had three different data sets, okay, with the different vibration level amplitudes, and we tried to understand what is the shape of the vibration, that is the amplitude, okay, and then we try to understand what are the different typical vibration levels which are there here, right? The kind of levels, and what may be the mean value, median value of that, and what would be the limits or kind of IQR data for that, right? And how would these shapes be visible in terms of skewness as well as kurtosis, and what would be our interpretation out of that, right? So as discussed yesterday, we understood that this is more of a normal data where it is trying to deviate from the mean value. So both mean and median are very much nearby to the zero value here, right? I'll just check. I think I don't have that presentation. I closed it off. It might be available in the code if I see here. Yeah, so we can see here. So it's very much nearby. And here mean is like very much higher compared to the median. So that shows the positive skewness here, right? Even again here mean is very much higher than the median. So it shows the positive skewness here. Similarly, even for kurtosis, we saw that the values are very high here for the amplitude, so that should represent the kurtosis value very much higher compared to this, because amplitudes were very 15 and this very 5, right? So it should be comparatively, kurtosis value should be very much comparatively higher than that. So now coming to the values to be decided, that whether it is going to be a failure or not, that purely depends on the domain knowledge. As I gave an example, there's a video from like say NPTEL where they show the gear failure and they decide the kurtosis factor for that, which is like they decided it should be 6 for gear failure for a certain system based on the experimental analysis, right? So then based on that they can say okay, the values for different data, if the kurtosis level is greater than 6, then most of the gear systems might fail. So that comes by experience and domain knowledge as well as with experimental and sorry, test kind of correlation with the data. And skewness basically just helps us to understand how the data is distributed and what would be the amplitude range and where it is shifted and how much data is occurring over there, right? Or how is the behavior of that. Like as I said, there are even certain transformations where we can convert the skewed data into normally distributed data. which will be helpful in analyzing the machine learning problem for us. And these are the formulas to calculate the kurtosis and skewness, right? Where you take the mean value as well as the like standard deviation value to calculate that with respect to the individual point. So yeah, I think I had other one data here. Should be that. So this was again a problem where we showed, I think we had again three different data sets, right? Cavitation, then normally distributed data, and imbalance again for pump related vibration data. So we understood again mean and median are very much nearby. So just because of just with median, mean and median, we'll not be able to do complete statistical analysis and we'll not be able to get the complete inference out of that. That's when we might have to do certain measures with respect to IQR or even with respect to skewness and kurtosis. So you can see that whenever there is a normal distributed data, even kurtosis will be more of normal distribution. Okay, but when there is some problem or defect, even it will affect the skewness as well as the kurtosis values for that. So we can see the amplitudes are very much higher, okay, compared to the normal pattern here, whereas we have a repeatability pattern due to imbalance. Maybe in rotary machines this repeatability occurs, right? Because in rotary machines it comes to the certain value each and every time it keeps on rotating at certain position, right? So that vibration pattern keeps on occurring every time. So the mean and median might be very much nearby to that, but that pattern also shows the very good distribution with respect to the normal distribution. But that doesn't mean that like it may not fail or something like that. So we'll have to check kurtosis as well as skewness value to check the impact, right? So then we discussed about the strength and limitations of the classical statistical methods. So how it will help us in interpreting the data, and how does it like how are, I mean, how does these measures are used in further machine learning algorithms, like especially in loss function. They use these as a certain like say base methods or like base terms to derive the formulas, right? And it's also used in hypothesis testing, or it can be used even with the conventional mechanical design of experiments to for design optimization, and try to analyze the different design suggestions from the design optimization algorithm and analyze that statistically. And coming to even limitations, we understood that this is more like useful for structured data or tabular data, and not much useful in unstructured data. And it has also an assumption that most of the data are linearly varying with respect to each other, and it's more of normally distributed, right? And even curse of dimensionality, where you might have be having 100 data, 100 features, but which is the right feature to understand, like say analyze the problem, or how do we get that 100 features to two to three features to like say get the exact output desired, right? So we can use certain PCA methods or something like that to reduce the dimensions of the data. So, and statistical methods are very much even computationally less, like say, it will take very less time to do the computation. So it's very much effective in that. But when it comes to larger data sets, it's very difficult to handle those things, right? And hope and then find the best fit. But it in ML, it is more of iterative and predictive methods today, where we try to understand the temperature data, anomaly of that, and even data, and try to understand the combined behavior of these two scenarios, right? And understand the correlation map, how temperature and stress are interdependent on each other. So we found that the correlation or the interdependence is very less, it's just 23%. So it may not be dependent on each other, or at certain temperature we know that the stress are very high or fluctuating too much. And we saw that even stress is getting stabilized over the period of time for a particular temperature range. So we even checked even in algorithm, just by changing the temperature data, how does it affect right here. So we can see that I just changed the temperature data here as a noise. Maybe I change to 10. So we can see how it is affecting, right? Even the ranges can be changed here, right? In the code. We'll say 150. So we can see how it is changing and how the stress will behave, how against stress there is a defect in the stress. So this might be even due to mechanical load, it's not only dependent due to temperature. That's why correlation matrix is also very much important for us to understand that, where we see even interdependencies between different mechanical parameters, right? And I think I have even shown other one where to understand what is the basic difference between statistics and machine learning, right? Where we could see statistical parameters. Okay, so I explained it here, I think. Yeah. So we have y is equal to mx plus c, and we identify the slope out of the standard slope equation, and then we try to interpret the intercept in statistical machine learning. So sorry, statistical methods, and identify the best fit method. Whereas in machine learning, we have a lot of test data. Okay, where it gets trained using the same linear regression method, but it is more of predictive method and keeps on iterating to find the best fit line. So we can see a slight difference there, right? And we identify what is the error percentage from certain metrics, where it is r squared or msc or something like that, mean squared error or r squared or something like that. So I think this is the recap of what we had discussed till yesterday, right? So any doubts till now? I hope YouTube this is getting recorded. So if any doubts in YouTube, you can just comment. I can just like say try to clarify that if it was little bit much faster. So if not, we can just continue with the today's topic. So Ajay, you don't have any doubts till now, right?
No, no.
Okay. So today's topic we'll just get still more deep dive on. Okay. So it is more of related to data analysis, right? So till now we understood what is mean, median, standard deviation, and all the stuffs, different statistical parameters. Okay. So this can be put into a section called as univariate analysis. The reason is because here we try to understand how, I mean, for each and every parameter, like say vibration or temperature, each and every variable or a feature, how these parameters are changing, right? Like say for this example, uh, I have some machine which is running. Okay, this is a normal distributed data, I mean, sorry, this is a normal data which is not having any defect. We do a FFT analysis, and then we have some abnormal machine which is having some different vibration pattern, and it might create some abnormality. Now for this I try to take a vibration data distribution. Okay, or even a temperature data distribution. So I'm measuring both vibration as well as temperature. Now it's showing normally distributed data for that, right? So for this analysis, what we have seen, this is more of called as a univariate analysis, because we are checking just one variable, maybe one variable at a time. So vibration I'm trying to analyze, vibration amplitude I'm trying to analyze, and I'm trying to understand what is the standard parameters, mean, median, standard deviation, skewness, and how it is impacting. Next, I'll go to other variable, which is temperature, and again I'll try to understand the mean, median, mode, standard deviation, and all those stuff. So it's like each and every variable, one variable, I'm trying to understand its corresponding statistical metrics, and trying to understand whether this is really impacting our like physics or not. Like just going back to the previous example, as we have seen here, we know at certain scenarios temperature might be affecting too much, and in certain scenarios stress might be affecting too much, right? For failure causes, or sometimes even mechanical load might be stress is a result of mechanical load. So there might be a number of reasons, so we'll have to analyze each and every feature, how it is affecting or where it is occurring, like which problem it is creating, right? So that's more of a univariate analysis, where we try to understand behavior of a single data or singular data, not singular, single feature. Okay, so how do we analyze? So there are certain metrics or plots where we can analyze. We can put histogram, or even like probability density function plot. Okay, this is a PDF plot. Red color is the PDF plot, and this is a histogram. Okay, so from this we'll be able to understand how much the vibration amplitude is distributed. Okay, how much is the density and all the stuffs. So just one example here, still more like say to understand a little bit of new flow. We often speak about digital twin, right? So kind of that kind of example, where you have some wind turbine, you get a vibration data, or you get even some temperature data or something like that. So this would represent that particular data set. You try to do a numerical simulation for that. You try to even capture the data, create a workflow for that, to analyze that through statistical metrics, what we have done, and try to build a quantitative data. I think we had discussed even in first class what are quantitative data and qualitative data, right? Which we can quantify. It is more of a quantitative data, which will help us to get the quality out of that. That is more of a qualitative data, right? So we can try to even build a surrogate system where we can even use the FEA data along with this captured data, which is live data, and build a digital twin and even improve the physical data. Sorry, physical, or build a countermeasure to improve the like say actual scenario if there is some problem, right? So that is more of a digital twin. So univariate analysis also helps in digital twin process where you try to analyze each and every parameter, and even try to build a FEA for that, create a surrogate model by defect, and try to analyze it better by statistical parameters. Okay. So any doubts still now for univariate analysis? So yeah, if no doubts, I think there are certain examples here. So you can check for univariate analysis how can we understand this, because same thing we had discussed when we had discussed the individual parameters, right? Mean, median, mode. What would it mean? How do we infer that, or what are the interpretations for these different variables? So next we go with bivariate analysis, where we try to understand the relationship between two variables. Like suppose in this case we have vibration amplitude and temperature. So we'll try to understand how the amplitude is affecting, how amplitude and temperature might be affecting each other. What are the relationships between those two? Or as in our previous case, where we try to understand the temperature and stress pattern, whether temperature load is really affecting the stress behavior, or is it mechanical load which is affecting the stress behavior. So we try to put the combined effect plot of that, right? So understanding a relationship between two different parameters is more of a bivariate analysis. Okay, so we have certain metrics for that, like say Pearson correlation or Spearman correlation. So there are different metrics to analyze that. So here we can analyze the linear, non-linear, or even certain uncorrelated behaviors out of that. Okay, so these are certain examples of that. So we can put a plot, scatter plot to understand the relationships between that. Similarly, when we have n number of variables and try to understand the relationship between n number of variables, that is called as multivariate analysis, where you try to put a correlation matrix between different parameters, like say now we have temperature, stress, mechanical load, everything, and you try to understand how each parameter is behaving with respect to each other parameter. So that is more of a multivariate analysis. So we'll have to go step by step. First, you analyze individual parameter, try to understand the statistical parameters out of that, get the inference out of that, then go to understand how each parameter is behaving with respect to other one, and then you can go with a higher dimensionality with the multivariate analysis. Okay, so this is more of a summary of that for univariate, bivariate, and multivariate. What would be the metrics to analyze that particular, let's say, data analysis technique, right? And what are the plots used, or commonly used plots to analyze this particular behavior, and these are certain examples of that. So I'll just we'll go through even certain exercises once you have understood, or you have if you have some data, right? I'll just open I think I had kept some links here. Yeah, so you can see here how does it vary, right? So this is more of a univariate analysis. How does multivariate analysis look? So you have two different parameters. There might be even local clustering of the behavior of the data, because you have two different parameters, right? It might be, as I gave an example of temperature and Young's modulus, it might be possible that for a certain temperature range, Young's modulus might be clustered in certain particular data, right? It might be orange. Yeah, if you take temperature is on x-axis and Young's modulus is on y-axis. So for a particular temperature range in this, Young's modulus might be varying only between this range. Similarly, for a certain temperature range, the Young's modulus might be varying only in this particular range. So even we might be able to fit this and convert this into a linear line here, right? Convert it into a linear relationship here. Put a linear regression and identify that, or convert the cluster into linear regression method by putting equation over there. So univariate analysis, as you can see, it's like clearly indication of like say one-to-one comparison, right? Think apart from that, it even helps us to show the direction how the relationships are evolving between two different parameters. Okay, it also gives us the direction of that. So yeah, so this is more of multivariate analysis, where I said we have different parameters, right? Like in this case, we have sepal length, width, petal length, and petal width. So this is for the flower, different flowers, right? So you're able to see this more of that histogram plot, right? So how each and every parameters are linked to each other and how it is varying with respect to each other. So this is more of a multivariate analysis. Okay, so now just to exercise, right? We have three different data. One is healthy data, two defective data. Okay, so first we'll understand univariate analysis. So this is univariate analysis where we try to plot the histogram of that. Okay, so you can see for healthy data how it is, and defective data how the stress ranges are changing, as well as little bit there's the skewness of that, and even see in box plots how it is varying, right? You can see this skewness here. More the outliers here, you can see how the skewness is shifting towards the left side, right? Here the skewness is shifting towards the other side because data is here, right? And these are the mean, median, mode or statistical parameters which we analyze for that, for healthy, defective, and severely defective. How it is changing, how this cortices is changing, right? Similarly, so since this for a stress, this univariate analysis is only for stress. Next, we can go with temperature. So even for temperature, we can do a separate univariate analysis, right? Again, we check it here. I think I just forgot to add one point. Uh, So we saw that kurtosis was negative, right? So what does that mean? So as per definition, you can say there is a very less extreme outliers, right? So we saw that kurtosis value is negative. So this will help you to understand the behavior. So for which defect it is negative? Second defect it is negative. So these values you'll have to analyze why it is negative, why it is positive, and all the stuffs. So we can have a next session where we can try to analyze in depth what does negative skewness mean, what does positive kurtosis mean, or negative kurtosis mean. So we can take an example and try to understand that still more better if you have any doubts. Okay. So next, as I said, this is more of a correlation matrix where we can plot and try to understand the different behaviors. In this case, we are able to understand how temperature is varying with respect to stress, or how vibration is varying with respect to displacement and all the stuffs. Higher the correlation, it means they are very much interdependent on each other. So you can try to eliminate one feature out of that. Suppose if you say temperature is very much dependent on displacement, like if the correlation is very high, like say 70%, 80%, then you can eliminate one of the feature because it means it is like kind of repeatability of the data. So it will also help us to even understand the clustering of the data. Like certain behaviors can be clustered, right? As I shown here. Yeah, where we have seen okay, not this one, yeah, clustering of the data, the cluster behavior. I gave a example of Young's modulus where we could see for here different Young's modulus and temperature ranges, there might be some clustering. So that is a even multivariate analysis. Okay, so any doubts till now here between univariate, bivariate, and multivariate analysis? uh, if no doubts, I think I'll just continue with the next concept. As I said earlier, okay, uh, we spoke about correlation, right? So what does correlation mean, right? So we understood up to these parameters. So IQR I'll take in next class. So but up to mean, median, mode, and all the stuffs we understood, right? Kurtosis, how to understand. So this one still more we'll try to go in depth. I'll try to understand or try to get some data sets where we'll try to understand why, how do we deal with negative skewness or positive skewness? What does that mean exactly, right? So these two I'll just remember to take up those things in next class. So coming to correlation, it is very much useful in bivariate analysis. Okay, so we can put a heat map or pay plot or something like that. So first, let me teach. Okay, before going to correlation, we have a term called as covariance. So covariance is also same term where we try to analyze between two different variables. So this is the formula out of that, where you have a mean value, and for that mean value you take the summation and take the product of that two different like say for two different mean values and two different variables, you take the summation of that divided by n minus 1. Okay, but now when you scale this or try to fit it between minus 1 to 1 or try to standardize it with respect to the standard deviation, then it becomes correlation. Okay, so covariance when it is standardized between minus 1 to 1, then that becomes correlation. Why is it so? I'll just show it to you. So this formula is basically this one on itself. Let us say, uh, yeah, you can see this, right? So we got this in this plot data distribution between Young's models and temperature, that covariance is minus 2593. So how do we interpret it? It is very difficult to interpret, right? It might vary randomly. It is because it varies from minus infinity to plus infinity. The covariance varies from minus infinity to plus infinity. But to get more of like say realistic interpretation, how does it vary? We try to standardize it or try to fit it between minus 1 to 1. So that's why correlation is just saying minus 0.99. It's like kind of minor, like say fitting the data or like skewing the data between a particular range. That's why. So in this we are able to see it better, right? Same plot, covariance it is showing 441.22. Same plot when I try to fit it between minus 1 to 1, I'm getting correlation as 0.87, right? So this is more interpretable for us compared to that, right? Yes, Ajay.
Is it like some kind of a normalization?
Yeah, yeah, normalization. Yes, it's called as normalization.
Yeah,
It's similar to in modal analysis we have, right, displacement normalization
correct.
and
Yeah,
yeah, mode normalization, something like that.
yeah, yeah. Displacement normally becomes one, so like
Yeah,
it will normalize between 0 to
yes,
1.
yeah. So next, now see, I can go still more in depth. So in correlation we have three types generally. Okay, positive, negative, and no correlation. What does that mean is, like, I have taken example of crack growth. Suppose if we have some crack, if the load is applied, the crack tries to propagate, right? So it means crack length is increased, right? So we say as the load increases, the crack keeps on increasing. So that's more of a positive correlation. Now suppose, so this is the case of tensile load. Suppose if I have a compressive load, it might possible that crack is getting arrested, right? So that will show a negative correlation for us. So it is minus 0.93. Here it is 0.96. So this is positive and that is negative correlation, where one variable is increasing and other variable is decreasing. So that's having a negative slope there actually. Similarly, there might be a scenario where load might be applied somewhere, but still crack is getting propagated, and that load may not be a cause for that crack. It means there is no correlation at all between them. So that's a no correlation. Sometimes it happens that it shows as a circle or certain ellipse patterns where the data itself is not related to each other. Okay, so there are even advanced methods in correlation. Okay, as of now I have discussed only Pearson correlation, what I've shown here. Okay, but this was very discovered, I mean, like say very early mathematical derivation, which was in 1896, the Pearson one. We are still using it. So this is a Pearson correlation. Then we had some upcoming advanced methods which is used even currently in machine learning to understand based on different applications or problem statements. Okay, because it has a drawback. Pearson is sensitive to outliers. Okay, and it always requires normally distributed data most of the time, and it doesn't want too much skewness. And it is used for continuous data and linear relationships. So those kind of drawbacks are overcome by certain other methods which are over here. So I'll not go in detail for all the other methods. Only if like you people are interested, I think then we can go when we start with machine learning subject on these. Like we can go with machine learning problem. We'll try to analyze this Pearson first in basics, Like say first we'll try to analyze with Pearson formulation, and with the same machine learning problem we'll try to even plot other correlation methods and try to see which one is better for our problem. Okay, so we'll go in depth in that particular scenario. But here what I wanted to show you that what does covariance mean, what does correlation mean, and what are the different types of correlation occurring, and why what would be the drawbacks of Pearson, and how it has been evolved up till now. Okay, and there might be even other methods, and how the formula changes, and how it might be useful for different methods. Like say for regression, Pearson might be holding very good, but it may not be holding very good for multi-class classification problem. So we'll have to understand which classification or correlation method is useful for different problem statements, and what are the drawbacks of that, why it is implemented, all those stuff. So I have just put it down over here as a table. So for what problem type, which method can be, correlation method can be used, and why it can be used, because what is its strength, right? So this gives us a perspective that how can we use which mathematical I mean what kind of mathematical method can be used to realize our data relationships. So yeah, I think that's up to this class today. Yeah. So if you have any doubts, I think we can clarify. So in next class, I'll just dive upon IQR and outliers and normality. And I think again, K-means, PCA, all these things are machine learning algorithms. So that we'll discuss when we start teaching on machine learning classes. So any doubts till now? I think I have other one paper here. Yeah. So even this paper is useful. So this on digital twin. So you can see currently which tools are getting used by which company, and yeah, for which applications, right? And even how FEA is important for that. You have the flow over here, real plant, digital twin of the real plant. So any doubts? If no doubts, I think we can close for the day.